Hello learner, greetings of the day. Let's discuss about the clipping window and the mapping from the clipping window to the viewport. So this concept we are going to discuss here. First, let's begin with what is exactly a clipping. So clipping is nothing but removing the portion that is not of interest. For example, if I consider one boundary and that boundary, say it is in a normal rectangular shape. So if this is my boundary, the object that I have inside this, say I have an object like triangle, a circle, a line and few points. So all these are the basic geometric shapes that is inside the boundary. Say for example, I have one shape that is somewhere something like this. One portion of the object is inside the boundary and the other portion of the object is outside the boundary. So now what is clipping over here? It is something like all the objects or shapes that comes within the boundary, that falls within the boundary of this rectangle. I'm going to finally generate the image of that, or I'm going to finally map that onto my display window. Suppose if I take this as my display window, you can just say that all the objects that lies inside the boundary will be displayed on the display window. So what are the objects? It is triangle, and then the line, and then the circle, and then the points there, and then one portion of the rectangle which is inside the boundary, only that will be displayed. So we can now say which portion is clipped off. There is a small portion that comes outside the clipping window. That portion is not displayed on my display window, or in other words, that portion is clipped off. Okay, so this is the concept of clipping, and I call this as clipping window. So when I say a window, usually a window will be in a rectangular shape. That is a standard size or standard shape of the clipping window, or clipping, you can call it as clipping rectangle. What if my clipping rectangle itself is what if my clipping window itself is in a complicated shape? What is the meaning of complicated shape? Suppose if I have a convex polygon, so can I call this rectangle as a convex polygon? So definitely this is a convex polygon. Why? Because you can say that it is in a regular shape, and if I start from a particular point, you can go through all the edges and come back to the same point without any distortion there. So you call it as a convex polygon. What if instead of convex I have a concave polygon? Suppose if the clipping window itself is of this shape, uneven shape, okay, clipping window is of this shape. So can I perform the clipping in a easier way? Can I process the clipping in a easier way? I cannot do that. Why? Because you can say the boundary itself is non-linear. It is not in a regular shape. It is very irregular. Since the boundary itself is irregular, I cannot perform the clipping in a desired way, or I cannot process the clipping as fast as the convex polygon. So usually we take the clipping window as the one which has regular boundaries or a linear boundaries. So convex polygon you should choose as a clipping window. Usually rectangular shape is a standard one. Okay, so that is about the clipping window. Now let's see how exactly the coordinates are defined, how exactly we can define this clipping window in the world coordinate system, or how can I set up weaving here with the help of this clipping window. We will see with the help of an example. So here you can see we can perform 2D weaving. So in order to perform the 2D weaving, a transformation is required. So what is the transformation? When I say weaving, it's nothing but rendering the image of an object on my display window. So it is this part, rendering the image on the display window. This is what we are speaking about. So weaving. So for setting up weaving, we have to do certain transformation. So what is the transformation that we have to carry out? It is always the transformation. It is from the world coordinate system. We have to transform directly from the world coordinate system and finally onto the screen coordinate system. So how to set up weaving coordinate system? First of all, within world coordinate system, within the world coordinate frame, we will see that. So once we set up the weaving within world coordinate, later we can think of transformation from world coordinate system onto the final screen coordinate system. So first we will see here in the image how to set up weaving within world coordinate. So first you set up the coordinate system, and you can call this as x-axis, or in other words you can call it as x world, and this is a y-axis or y world, and you represent this coordinate system as world coordinate system. And let me take one point here within the world coordinate system, and that point is given by x0 comma y0. So about this point now, I am representing the clipping window. So how is my clipping window initially? You can just see here, my clipping window is of this shape is rectangle, but it is slightly oriented. So what is that actually? My clipping window is oriented, and you can see my clipping window has certain coordinates there. Okay, and let me take that coordinates as, this is an object, or you can call it as simply a rectangle with the boundary. So you call this as a minimum boundary x min y min, and this as a maximum boundary, that is x max y max. So lower left corner and the top right corner, you can call it as the boundary of the clipping window. Now you can see this window itself is represented with the help of one coordinate system. So what is that coordinate system? You can see this is the weaving coordinate system. So you can see this weaving coordinate system has an origin, and about this point you have represented the clipping window. Now how to transform this weaving coordinate system onto the world coordinate system? So for that you have to perform some actions. So what is that? You can now translate slowly this particular window as it is onto the origin of world coordinate system. So what is the transformation technique you are applying? It is basic translation. So what is translation? That is moving or displacing a particular object onto a new position. So you need certain translation factor. So by that displacement factor or translation factor, first move this window to the origin. So origin is with respect to this world coordinate system. So once you get this onto the origin, later what can you do? Can I work with this oriented clipping window? No, I have to now again shift the position, or you can say I can now orient or rotate this particular clip window into the in a particular by an angle theta, by a suitable angle theta, I can orient or I can rotate this particular clipping rectangle. But where am I performing this rotation? It is not here in the original position. I am first translating it to the world coordinate system, that is with respect to this origin. Now I am going to rotate by an angle theta. So after rotating this rectangle by an angle theta, I'll get the rectangle in a standard shape and in a proper you can say within the proper coordinate system, in a proper position. I get the rectangle, clipping rectangle. You can see the figure of that in the next slide. Now you can see here, as I already said, this is my original coordinate system, weaving coordinate system. What did I do now? I have just translated. See, this was the position about which we had represented a clipping rectangle here, which was a little oriented there. So you get as it is, you translate as it is to the world coordinate system, that is the origin of the world coordinate system, and you can see as it is, that is moved here. So this old origin is shifted to the new origin with respect to world coordinate system. So after translating, now you are ready to orient or rotate. So rotation is applied now here. You can see rotation is done by an angle theta. So after rotating, you can see the rectangle will be in a proper position there. Okay, so now your clipping window is ready to perform clipping with respect to world coordinate system. So this is the first step that you have to carry out before you map any image onto the display window. First, this world coordinate representation is important. Clipping rectangle should be represented within world coordinate system. Okay, so you can see these two steps: first applying translation and then applying rotation. So mathematically, how do you do this? Translation is nothing but setting up translation matrix. So apply translation matrix first to move to the world coordinate origin, and then apply rotation by an angle theta to align your clipping window along the axis, that is x coordinate, x axis, x world axis, and align the rectangle along y world axis. So once the alignment is done, now you are ready for performing clipping. You can understand it in a better way. Now along with the clipping window here, I have shown an object also. So you can see this is the original clipping window in the old position. This rectangle is actually, this is actually a clipping rectangle which is exactly in a rectangular shape. Okay, this is a convex polygon there, and earlier see the rectangle was something like this. This is a weaving coordinate system, and you can see an object here is a triangle, and this is a point about which now you can perform any transformation, maybe about rotation you can apply about this point. And this is actually, whatever is shown here is a vector v about which you can perform the rotation. So what is this vector? It indicates the direction of rotation. You can orient counterclockwise, that is anti-clockwise, about this vector v, and this indicates the direction of rotation. Okay, so now this is the original object within the clipping rectangle. Now what am I supposed to do before I orient the object? I have to first translate. So if translation is done, and the translation is done, so which point is translated? Actually, this fixed point about which you are rotating is now first translated to the origin. Remember, the fixed point is shifted to the origin, because about this fixed point only I have to rotate the object. So you cannot rotate the object directly over here in the original position. So once you translate that fixed point onto the origin, you can see here the just translation we have done, not it rotate, we have not yet rotated. So there is one image missing here. What is that image? Orient the triangle as it is, you are translating it to the origin. So this fixed point will shift to origin. Now what is left out? Next you have to rotate that particular object. So how are you rotating? By an angle theta about this vector v, so that now the triangle will be aligned with the axis x world axis and y world axis. So this is shown after rotation. So this is the triangle now which is rotated about this fixed point. Now fixed point is shifted to origin, and about which, about the vector v in an anti-clockwise direction, you orient the triangle, so that now the triangle is aligned with the axis x world axis and y world axis. And you can see here the clipping rectangle also is oriented. So this is the position of the rectangle and the object inside the rectangle. So now we are ready. Now the clipping can be performed, and now we are ready for mapping onto the viewport or onto the display window. We can now move on to the next concept. So what is it? That is the normalization or the normalized window and viewport transformation. So normalization is performed first, and then the transformation is carried out. Transformation is now mapping from the clipping window onto the viewport. But before mapping from the clipping window onto the viewport, there is in between something called as normalization which has to be carried out. What is normalization? We will see that. See here, first the viewport coordinates, if it is in the range between 0 to 1. So what is that range? 0 to 1, so that the viewport is positioned within the unit square. So 0 to 1 boundary, it is something like this. See, assume there is one viewport, there is a rectangle there, okay, and the boundary for that I'm going to represent it as 0. What is that boundary? Left is 0, bottom is 0, right is 1, and again top is 1. So here this became a square with the boundary 0 to 1. So now I am assuming one boundary within this limit. So what can I do now? First I have my clipping window. Clipping window boundary is of your wish. You can set up any boundary for your clipping window. So once your clipping window boundary is set up, what you can do later, you can map onto the normalized square, or you can convert this clipping window onto a normalized square in such a way that your boundary now will be changed to, or it will fall in the range 0 to 1. So once this normalization is done, now you are ready for mapping onto the viewport. So now you are mapping this normalized square, or the object within this normalized square will be mapped onto the viewport. Okay, so this can be done. Now we will see how to do this with the help of matrices. Okay, so first mapping the clipping window onto the normalized viewport. So how this first stage is done? Clipping window to normalized viewport. You just see here, I have a clipping window represented, and I'm representing this clipping window within which coordinate system? It is within world coordinate system. And you can see here the boundary of the clipping window is, see, lower left corner is x, w minimum. W represents world coordinate system. So this is the minimum boundary, x w minimum, and this is the maximum x boundary along x axis. You can see this is the maximum boundary, x w max. YW minimum is again with respect to y axis, this is the minimum boundary, and this is with respect to y axis again y max, this is the maximum boundary of y. Okay, so now you can see here, this is the clipping window representation within world coordinate system, and I'm going to take a point here within the clipping window about which now you can say that I can translate this clipping window, or I can rotate this clipping window about one fixed point here, and that fixed point I'm going to take it as xw and y comma yw. Now I'm going to map this clipping window into a normalized viewport. Remember, the normalized viewport is the one with the fixed boundary. What is that fixed boundary? Fixed boundary can be something like this. It can be, by default, usually the fixed boundary will be something like this. The lower limit is -1, that is x minimum, y minimum is -1, and x max and y max will be +1. So usually the standard size for your normalized viewport falls in the range -1 to 1. Okay, so now you can see I'm mapping this clipping window to normalized viewport. So what is that I'm doing? You can see the size is reduced, right? So first of all, I have to perform scaling. So scaling is reducing the size of the clipping window. So how are you scaling? That scaling is done about this fixed point xw comma yw only. So about this point I'm performing scaling. I'm scaling to -1 to +1. The scaling factor is also given to you, and the point also is given to you about which you are scaling. So once the scaling is done, next what am I supposed to do? I'm supposed to translate now. So first is scaling, and next is translation. So what is this translation that I have to carry out? This translation is nothing but move the position, that is from xw comma yw to xv comma yv. So it is this position that we are translating. So now the new position that we obtain within the normalized viewport is xv comma yv. So how did we obtain? That is obtained after translation. So what is translated? xw comma yw is translated to a normalized window, normalized rectangle, and the new position there is given by xv comma yv, which is obtained after translation. So remember the two steps you have to carry out. First step is scaling, that is reducing the size of this clipping window to a normalized window. Next, it is this translation that you have to carry out in order to move the fixed point, that is from xw comma yw from the world coordinate system to xv comma yv, that is to the normalized viewport. Okay, so now this basic, whatever the two steps we have carried out, we can show it with the help of few equations. See, to transform the world coordinate point, that is this world coordinate point, into the same relative position within the viewport. So which is the viewport? It is this viewport. You can see the same relative position within the viewport with respect to xw comma yw. So how to do that? We can do that with the help of these equations. First, you are representing this viewport now. So you can see xv minus xv min. So what is this? Xv comma yv is a fixed point, and xv min is this point, yv min also is this point. Okay, xv max is this point and yv max is this point. So you can say now xv minus xv min divided by this one. What is this relative position with respect to window? It is xw minus x, sorry, it is, I'm sorry, it is this. I'm just saying the numerator part and the two positions. So what is it? Xv minus xv min, that is xv minus xv min with respect to viewport. What about this? It is xw minus xw min with respect to world coordinate system, with respect to clipping window, xw minus xw min. So both the numerators you can see, and what is the denominator there? It is xv max, sorry, it is this xv max minus xv min, xv max minus xv min. So it is this part, and then what is that here in the RHS? It is xw max minus xw min. Okay, so this is with respect to the x coordinates to calculate the relative position. And what about the y coordinate calculation? Again in the same way, yv minus yv min, yv minus yv min divided by yv max minus yv min. Okay, so this gives you the position with respect to viewport, which is equivalent to, or which is equal to yw minus yw min divided by yw max divided by yw min. Okay, so these are the two equations to obtain the relative position, okay, within the viewport. So once these two equations are done, now I can rewrite these equations, rewrite this with the in the form of two equations. So this first part, this first one, I can just do the cross multiplication and I can rearrange it, and I can write one general equation something like this: xv is equal to sx into xw plus tx, whereas the second one I can rewrite it as yv is equal to sy into yw plus ty. You may wonder what is this sx and tx, which was not there earlier in these two equations. I'll tell you what is it, sx and tx. Yes, so you can see there I had this equation earlier, these two equations earlier, these two. Yes, so now I'm going to consider sx there. In my general equation I have considered a factor called sx. What is this sx indicates? It indicates a scaling that I have performed. As I showed in my previous figure, what was that? First the scaling has to be performed, so reducing the size of clipping window to normalized window, so that scaling is performed. And what is that scaling factor there in the equation? It is given by xv max minus xv min. After cross multiplication, this goes here onto the numerator, divided by xw max minus xw min. That's all. So this has gone to the numerator. So xv max minus xv min divided by xw max minus xw min. That is our scaling factor along x. What is scaling factor along y? Similarly, yv max minus yv min divided by yw max minus yw min. So this became the scaling factor along y. So I have the two scaling factors along x and y axis respectively. Now I have the next factor. What is that? After scaling, what do I have to do? I have to translate the position xw yw to xv comma yv. So what is that translation factor given by? Translation factor tx is given by, with respect to this equation, you can see it is xw max minus xw min. here minus xw min minus into xv max. Okay, so we can just rewrite that, and just this is a small adjustment and all that which is done. Okay, just to show the scaling factor, translation factor, you are translating to a new position. Next, dy is given by yw max into yw min, v min minus yw min into yv max divided by yw max minus yw min. So this is a translation, that's nothing but the movement of the point from w max xw comma yw to xv comma yv. Okay, so translation is done. So these are the two steps that we have carried out, scaling and translation. And I can write a general matrix, that scaling, whatever we have performed, I can write it in the form of a matrix. Okay, and the scaling matrix would be a two-dimensional matrix. You can see it's, why do I call it as a two-dimensional matrix? See, I'm performing scaling along x and y. What about the z value? It is 1, so 0 0 1. So I call this as simply two-dimensional scaling factor where z value is equal to 1. And you can see what is the scaling factor. Along x is sx, along y is sy. So the first row indicates the scaling along x, second row indicates scaling along y. So sx is 0, and this is the scaling factor about which you are scaling, and this is sy, this is a scaling factor about which you are scaling. Okay, so once the scaling matrix is set up, now two-dimensional translation matrix also I can set up. So first row indicates translation along x, second row indicates translation along y. Okay, you can see translation, always the third element indicates the displacement factor. Remember, in translation 10 tx 01 ty, what is tx? It's given by xv min minus xw min. And what is ty? Yv min minus yw min. Z value, the third row indicates z value, which is equal to you can say z value is equal to 1. Okay, so that's done. So next, general matrix representation. What is composite matrix representation? I have to multiply these two matrices in order. So what is that? In order means always I have to go for post multiplication. So first I am performing scaling, and then I perform this translation. So this is called post multiplication. So first you take the scaling matrix, which should be multiplied by this translation matrix, and the resultant that you get it in this format generally. So sx along x 0, and this is a translation factor along x. Then second row indicates y, translation factor, and this is a displacement factor. And the third row is 0 0 1. So this is a general matrix format to perform this transformation from the window to normalized viewport. Okay. Now let's see an alternate approach to do the mapping of clipping window. So this is an approach where you map a clipping window first to a normalized square, and then you map this normalized square onto the final screen, that is onto the screen display window. So what is that? You can just see this diagram. So here first you transform the clipping window onto a normalized square. So here in this normalized square, you can perform the clipping also. What is that clipping? So you can see this is a clipping window, initial size of the clipping window, and this is a point about which you can perform the clipping. What is the point? Xw comma yw. Now you are mapping onto the normalized square. So this normalized square is of dimension, or it falls in the range -1 to 1. So left is -1, bottom is -1, rightmost end is 1, and top is 1. So -1 to 1. So this is a boundary. And now the point here about which you are clipping is the new point x norm comma y norm. So this mapping should be done. So clipping window is mapped to normalized square, and now here you perform the clipping with respect to -1 to 1. Once your clipping is done, next you can now map this normalized square or normalized window directly onto the screen. So what is the screen here? Screen on which the viewport is defined. So this is a viewport onto which you're finally displaying or rendering the image. So here the point about which you're displaying or rendering or performing clipping is xv comma yv. So this is your viewport on which finally you're displaying the image. Here no clipping, this is displaying the image. This is a space on the screen. This is a space on the screen. Okay. whatever you have clipped, that portion which lies inside the window will be finally rendered on the screen. So this is a viewport. Okay, you can see this is a series of mapping, and you can see that now in the form of matrix. You can just see here the matrix is represented, that is the first part. What is that? Mapping from window to normalized square. The first part of mapping, clipping window to normalized square, and that matrix is given by 2 divided by, why 2 here? I'm assuming that the clipping window here is of size 2. Okay, here I'm sorry, the normalized square here, we have assumed it as the of size 2. So normalized square, I'm assuming it as of size 2, minus 2 to 2, and again here bottom is also minus 2 to 2. This is the size. Okay, so now here you can see 2 divided by xw max minus xw min, and this is the factor there. Okay, so 2 divided. So this is a mapping done. That's the first step. And now what is the last step? Mapping from normalized square to the viewport. So what is that done? So you can just the reciprocal, you can see it is now with respect to viewport, xv max minus xv min divided by 2. Here yv max minus yv min divided by 2. Okay, so this is a matrix done for the next step. And you can see finally the output image. This is actually the screen, and in the screen you have a small rectangle. You can see one portion of the screen which is acting as a display window, and again inside that display window, by default entire space of the display window you can take it as a viewport, or else you can define a viewport inside this display window. And you can see that viewport here, a small region, that region is invisible, which is shown in a dashed line, and inside that invisible region of viewport you have the image displayed. So from where did you get this image? Directly you have mapped from normalized square to the screen. Okay, so this is your viewport, invisible window. Inside the display window is the viewport, inside which your image is displayed. So this entire region is computer monitor screen. Okay, inside the monitor screen, one portion you have defined as display window through OpenGL function create window, glad create window, and inside that display window again one invisible portion you have, that you have defined through viewport. Okay, that is defined with respect to viewport. Inside that viewport now your image is displayed. So this is actually your final image that is rendered on the screen.